Hi friends, the next important signal to work with is sinusoidal signals, which is the fundamental signals or fundamentals under harmonic signals. So that's a sinusoidal. So in the continuous time version, it looks something like this: sinusoidal or cosinusoidal. It keeps oscillating up, down, up, down, up, down with a constant frequency. So usually it is referred with a frequency and phase, and it can be either sinusoidal or cosinusoidal. And the radial frequency omega is 2 pi f, where radial frequency is a vector rotating around the origin of unit length with a frequency of f revolutions per second. Then omega will be 2 pi f radians per second, and it is periodic if the frequency is rational. That means if we represent frequency in terms of some numbers, then yes, it is periodic, and that's fundamental in communication and control systems. And we make use of sinusoidal as orthogonal signals, as we discussed earlier. Orthogonal signals are the signals which don't have any component in parallel to them, so they are orthogonal to each other, which means the inner product of two signals, if it is 0, then they are orthogonal. Here the red one indicates the sinusoidal of value x, whereas y, the green w1 represents the sinusoidal of double the frequency, that's a double 2x. And if you just find the inner product of this, it's always going to be 0, and that way we can say that over one period the sinusoidal integral frequencies of sin x are orthogonal to each other. So sin x is orthogonal to sin nx, where n can be any integer, and that way we can have orthogonal signals, and these orthogonal signals can be used to represent any other signal. As discussed in the vector analysis, the orthogonal vectors are the basis functions for defining any vector in the vector space. On the same grounds, the sinusoidals can be the basis functions for defining any signal in the signal space. So that's some details about the sinusoidal signal. Many more details to continue. Thank you.